to start now when people already, gradually come in. And good afternoon, everybody, and so welcome to this week's Heavy Ion Tea. And we are very pleased to have Ivan Viteb from Los Alamos Lab to give us talk about jet production in EA collisions at future EIC. I think everybody here should be familiar with, very familiar with Ivan, but still let me just briefly introduce him. He got his PhD from Columbia, working with Miklos at 2002. And from there, he went to Iowa State University, working with Jamie Chu for 2 years. And then he went to Los Alamos in 2004 as an Oppenheimer fellow, postdoc fellow. And afterwards, he was promoted there, and then he became now senior scientist there right now. For his work, he actually got his early career award on 2009 from DOE. So we are very thankful for him to join us today and talk about his work about jet in EIC. Please go ahead, Ivan. The speaker is yours.
Thanks, Shinyan. Thanks for the invitation. So as I said, I have to minimize the screen, but I'm pretty sure I also know most of the people in the audience. So let me just turn, all right. How do I turn my camera off so that we save bandwidth? So let's do that. And okay. So I'll go from here. So as Shinyan said, I'll talk about jet production in EA collisions. And here is the plan for today. I'll talk briefly about the formalism of understanding the formation of Parton showers in cold nuclear matter. Then I'll discuss briefly meson production for two reasons. First, meson production is interesting in its own right, but also we have experimental data from the HERMES experiment, and this helps us get some constraints on the transport properties of nuclear matter so that we can make somewhat educated predictions for electron-nucleus collisions at the EIC. And I'll end up with a comment on EIC, but also other proposed facilities. And some illustrative references are given here. The works done with Hai-Tao Li, Zheilong Lu, Matt Sievert and Boramion, supported by the TMD topical collaboration and the LDRD program at Los Alamos. So, okay, I have to click here. And so probably for most of you, there doesn't need to be much of a motivation. The EIC is the next generation nuclear physics facility in the US and the world. And it will answer fundamental questions about the origin of mass and the role of gluons, the internal landscape of nucleons and nuclei and the 3D tomography, the phenomenon of gluon saturation, and also, very importantly, the transport properties of large nuclei, cold nuclear matter, and the physics of hadronization. There have been a lot of new developments in the area of jets and heavy flavor, and I'll focus on their calculations, specifically in electron-nucleus collisions. There are also other observables loosely related to jet physics, such as energy-energy correlations, and from which we can learn about TMD physics, but I'll not have time to get to them. They're in the backup. So the formalism. Now, the theoretical framework in which we study those phenomena are the framework of in-medium energy loss or in-medium Parton showers. And the phenomenon of jet quenching, which arises from such interactions in this framework, is well established. In fact, not only theoretically, but experimentally. What is shown here is now a very old figure, I think by the Phoenix collaboration, which shows the suppression of pions and atos, as opposed to lack of suppression of weakly interacting final state objects, such as direct photons. And, it has, as a verification of this physics, it made its place even in the ANSAC long-range plan about, I think it was about 15 years ago. Now, what we are really interested for the purpose of this talk is the phenomenon where a virtual photon, let's say at the EIC, strikes a quark which propagates through nuclear matter. This is the gray box, interacts with the scattering centers in the medium. In cold nuclear matter, those would be nucleons via gluon exchanges, primarily in the transverse momentum, and leads to the induction of Parton shower. That's the medium-induced component. And one way to formulate this problem is in terms of effective field theories by introducing those interactions in the Lagrangian of QCD, let's say effective theories of QCD such as soft collinear effective theory. And so this is a rather universal way. Because the interactions are off-shell, those little gluons here called Glauber gluons are off-shell, we can essentially combine their effect in a potential. Those would be a scattering potential in the medium. Thereby, we separate the perturbative physics of the interactions in the Parton shower from the non-perturbative physics of the medium. Typically, we don't have first principle, we cannot perturbatively evaluate the properties of the medium. We can use non-perturbative methods or extraction of properties, but it's a nice way of separating what we can compute and what we cannot really from first principles, kind of easily perturbatively. Now, what we really need to compute now is the in-medium splitting functions, analog of the Autorelli-Parisi ones, which take us from the hard scattering to the long-distance physics of hadronization. And they're essential both for higher-order calculations, such as NLO, or resummation, the in-medium Parton showers and evolution. And here is one example how we can do this using the technique of Lightcone wave functions. It's often used in saturation physics. If we have a simple vacuum splitting process of a quark into a quark in a gluon, we can write the amplitude for this process. This is a normalization. This is the quark propagator. And these are the various initial and final states. When we square this, trace some over polarizations and supply the relevant phase space, we can get the Autorelli-Parisi splitting kernels. The kernel includes both the longitudinal momentum fraction x as well as the transverse momentum. And this is nice because the Lightcone wave functions can provide simultaneous calculation of both massive and massless big-lab splittings. And of course, they're checked against the media, the existing literature. Now, what we're really interested in is to calculate what happens from when we have interactions in the medium.
Ivan, question?
Yeah.
What do you mean by a massive splitting? Is this a heavy quark,
heavy quark,
or do you mean
for a heavy quark? So we can essentially calculate in one step both for light and heavy quarks. The reason for which I emphasize this is because when we originally started those calculations, like in 2011, we would construct an effective theory. And so it was typically constructed for a light quark. And then to calculate the heavy splitting functions, you have to construct a different theory for the heavy quark. And here you can kind of just get it for free if you want. M here is simply the mass of the heavy quark. Sorry, I didn't clarify that.
So does virtuality play it? Well, you have virtuality in this slide. So when you talk about massive, you're not talking about virtual.
No, I'm not talking about virtual. The exchanges are virtual. Virtuality plays an important role, and that's the point of this slide.
Okay.
So let me get to it. So what we do is the opacity expansion or the reaction operator approach. We can generalize not only for the energy loss process, but for the full in-medium splitting. And the way in which it works is to generate one power of the elastic scattering cross-section in the medium. You need two gluon exchanges. And you can put it on the two sides of the T equal infinity cut. Those would be the direct terms, or one side. Those would be the double Born or virtual terms. And there is kinematics and the amplitudes and the potential involved in those scattering centers. The propagator's height in the Lightcone wave functions, but then there are those interference phases. These are the Landau-Pomeranchuk-Migdal interference phases. And this is where virtuality plays a critical role. Those phases are essentially virtualities. And they come in two ways. The first way is just kind of when we have scattering, we can have some virtuality imparted on the Parton. Then when we have a splitting, the splitting itself also involves some non-zero virtuality. And we have the combination of both when the interaction happens, let's say, after the splitting. So this is where the non-trivial Landau-Pomeranchuk-Migdal effect hides. Now, with those diagrams that I've shown here, if we calculate them, we can recover all the splitting functions to first order in opacity. That's one correlation between the hard scattering and any subsequent scattering in the medium. And we can take the soft balloon emission limit and recover the energy loss result going back to Miklos-Joulasi et al. In 2001. And just to give you a sense how a full in-medium splitting function looks like, here is one result, and this is only the medium-induced part. Now, it is proportional to the Altarelli-Parisi splitting function in the vacuum. It depends on the properties of the medium. Lambda glue here is the gluon scattering length. So if we don't have a medium, you can think of lambda going to infinity. So this whole contribution will just disappear. It depends on the momentum transfers. And then there's the kinematics. All of those vectors represent different kinematic combinations of momenta that we have. And omega are the interference phases. Now, there are some nice properties that we can prove rigorously. The total splitting function or splitting kernel is the sum of the vacuum one plus the medium induced one. It factorizes from the hard part. Its gauge invariant, as I discussed, depends on the properties of the medium proportional to Altarelli-Parisi. What is most important, however, is that the in-medium Parton shower, what this thing here represents, is softer and broader than the one in the vacuum. This is to say that there are even more softer branchings than in the vacuum ones, and it's larger angle than the vacuum Parton showers. So because of this property, the in-medium splittings, the Parton showers, will give additional contributions to the components of any factorization formula. For example, if we have hadrons, we'll have additional scaling violations and in-medium evolution. If we have jets, we'll have additional components to the jet functions. And what is shown here is just one example that this actually works. The pink band is the prediction from the in-medium splitting functions together with medium-induced evolution of the fragmentation functions. And this is how it compares to other energy loss approaches and to the CMS data. Those are actual predictions, by the way. Now, from the diagrams that I showed, in addition to calculating the first order in opacity, we can extract the reaction operator. This is to say, the effect of one additional correlated scattering in the medium. And for the purpose of solving the problem, we found it useful to separate those possible interactions into initial state, where they happen prior to the Parton splitting, initial final state, and the complex or the conjugate one, and also final state here in the first line. And so we decomposed the amplitude, or it's not the amplitude, it's actually the square of the amplitude, the splitting probability in those components. And we found they're evolved by an upper triangular matrix. So this allows us to solve this equation. You start from the initial state interactions where there's only one component, solve for it, substitute, solve for the next one, and so on until you get all components and you sum them. And we've actually written, even though it looks complicated, we've written a mathematical code where we're able to solve to any order in opacity. The only problem is that because we keep exact kinematics, the expressions are very long. So to second order, it's more than 5 pages. We have still done preliminary investigation of second order in opacity contributions to the leading first order one. And here are a couple of differential results. On the left-hand side, we have the splitting spectrum versus the momentum fraction x. And on the right-hand side, we have the angular spectrum or the KT spectrum. That would be the transverse momentum of the splitting. You see that, for example, the effects are noticeable, but they're not gigantic. They do not qualitatively change the behavior. We have a little bit enhancement of democratic branching around x⁴, and a little suppression for soft and very hard splittings. Also, the broadening is qualitatively similar. It's just kind of a little bit broader distributions. We believe that for phenomenology, the average of the first and second order, which is given by a gray line, would be something good. But as I said, those calculations are very numerically expensive. So what I'll be showing still uses the first order in opacity calculation. And as you can see, the differences are not that dramatic. They're, reasonable. Before I move to phenomenology, I just wanted to mention something that might be interested to you. So the last thing that we have done is look at the effect of inhomogeneities and fluctuations of the medium and medium motion. Now in the QGP, this is very well motivated. It's easy to understand. We have transverse and longitudinal expansion. At non-zero impact parameter, we have rotation. This is the V1. We have fluctuations. In cold nuclear matter, we also have some motion. We have orbital motion of nucleons. We have a breakup of the nucleus in large Q² process. We have color charge fluctuations. And so what we did are two calculations of effects on the jet propagation and broadening and the effects on the radiation and branching. And we did this like to linear order in velocities and gradients. And here are a few illustrative results. What we found is that for the case of jet propagation, in addition to the Mohr multiple scattering, which gives like a Gaussian and then a power law tail, you have non-zero deflection, so to speak. You have a non-zero first moment, which is clearly proportional to the velocity of the medium, the number of scatterings, and is suppressed at large jet energies. So if you want to look at the effect of flow or medium deflection, you'd better be looking perhaps at a few GeV hadrons or jets up to about 10 GeV. Above that, I don't think it's going to work. We've done the same for radiation, in fact. And as you can see here, K per over XC, that's just the angle of the emitted particle. It's the largest for soft, large angular particles. And once again, we've calculated a specific moment to illustrate it. And so it is proportional to the velocity and the number of scatterings, and is largest for the softest particles. That's a little bit of a digression. I think it should appear on the archive tonight, but we plan in the future, whatever this may mean, it might take a couple of years to investigate the phenomenology. All right, so that was for the formalism. Let me now move first to hadrons. And why study hadrons before studying jets? Well, that's the only observable for which we have data, kind of in DIS on nuclei, admittedly at much smaller center of mass energies. It can allow us to constrain the properties of cold nuclear matter within our formalism. Different formalisms will give slightly different properties. And it will allow us to identify the regions of phase space and center of mass energies where studying those effects would be most productive. In other words, calculation of jets is more computationally expensive. We don't want to be computing in areas where the modification will be zero. So let's do this first for hadrons. And finally, hadrons themselves can provide some differentiation between the two paradigms, hadron absorption inside nuclei, or energy loss, or generally speaking, Parton showers, and hadronization outside. Now, I personally think that, well, it's not that I think about it, I think it's objectively true, that this would be more relevant for the EIC, because simply the center of mass energies and the boosts, the energy of the hadrons in the rest frame of the nucleus are much larger than in the fixed target HERMES experiment. So this would be what's more relevant for the EIC, but it would be important to investigate, of course, both paradigms. So very briefly, as I said, I'm not going to talk about electron-proton collisions. They're just a warm-up exercise in calculating something for electron nucleus. We've done calculations up to next to leading order. Here are examples for different center of mass energies, different electron and proton or nucleon in the nucleus combinations in two different PT ranges. What we find is that the K factors are between 1.5 and 2.5. These are the analog K factors. And we are also calculating as a function of transverse momentum relative to the collision axis. We don't fix Q square per se of the process. For this region, the Q square can become small, and in which case the electrons become sources of Weizsäcker-Williams photons, which can also interact and give a contribution up to NLO. And it's, a reasonably large correction. So that's what we have taken into account as our baseline. And with this, we proceed to study the modification in the medium. So the modification, just as in the example that I gave for hadrons at CMS, would be given by the in-medium evolution of fragmentation functions. Now, in principle, this is not the only way in which you can do it. You can put it in the hard part, or you can take an intermediate scale, put some of it in the hard part, and some of it in the fragmentation functions. That's simply too much work. So we've done the scale choice in such a way that all of the effect comes from the in-medium evolution of fragmentation functions. And what the effect is just an illustrative example. This is a gold nucleus. The fragmentation function of a light quark into a pion, charm quark into a D meson, and the big quark into a B meson. That's the medium evolution divided by the vacuum one. For pions, we always see the additional scaling violations always lead to a suppression, except at very small values of the momentum fraction Z. This is this additional contribution from the soft Parton showers. For C and P quarks and D and B mesons, the situation is very different. We start with a very large suppression, but then very quickly we go to a significant enhancement and intermediate values of Z. And this comes here from two things. First, of course, is the additional evolution, which reshuffles things, but it's because of the specific bell shape of the heavy quark fragmentation functions. And finally, when we go to very small values of Z, we see this extra additional enhancement on top of the one from the shape. And this is from the soft partons. The reason for which here it's even more visible than for the pions is that at small z, the pion fragmentation functions are growing, but the heavy quark fragmentation functions are very small. So the question is whether we are going to observe this, of course, in the experiment later in the EIC. But let me first go to HERMES. HERMES was a fixed target experiment at DESY using the HER beam of 27.6 GeV. And what HERMES measured was this double ratio, let's say multiplicity of pions divided by the multiplicity for the inclusive electron scattering on the nucleus, divided by the one on the deuteron. And the reason for which they did this double ratio as opposed to single one is to eliminate initial state nuclear PDF effects, which will already be reflected in the inclusive electron scattering. So applying the technique of in-medium deglap evolution, having calculated the in-medium splitting functions, including geometry and path lengths and whatnot, for the different nuclei, such as krypton or xenon, which I don't show here, we are able to describe the different differential suppressions as a function of the momentum fraction, the momentum of the strict parton in the rest frame of the nucleus, nu, and the momentum fraction z of hadronization. So when we see those effects, which are clearly large and very well measured, we know that they come from final state interactions. And in our particular framework, the Q hats extracted, now just quote the one for the quarks, are about 0.05 Jeff square per Fermi, which is right in the middle of the range of what various formalisms who have previously addressed this data have extracted. And the band corresponds to a variation. So let's now do the calculation of meson suppression with those constraints and this formalism at the EIC. And we again define a double ratio for the exact same purpose, to try and minimize initial state nuclear PDF effects. So that would be the multiplicity or cross-section of hadrons versus PT and rapidity, and perhaps the fragmentation fraction Z, divided by the cross-section for a large radius inclusive jet. The idea of the large radius is to not have final state effects, that all of the in-medium shower will be contained. And for this purpose, we can do essentially a lowest order calculation. An equivalent way would be to precisely calculate where the electron will scatter at backward rapidity and normalize by the scattering of electrons just in this particular rapidity bin, and we've done that, and it also works. So those figures illustrate what we found. If we look at small center of mass energies, such as the ones illustrated, and forward rapidity, that would be the proton or nucleus rapidity going direction, we see very large suppression for light particles like pions. This is a factor of 3 suppression. It's actually huge. And then for DMB mesons, the suppression can also be large, even though at low PT, it becomes somewhat smaller. Now, on the other hand, if we go to large center of mass energies and backward rapidity, as you can see, for DMB mesons, it's essentially 0 modification. And for pions, it's maybe, 10% or at most, 15, 20%.
Ivan, can I try and clarify? Now you are looking at this in a different frame, right? Your PT actually really transverse momentum to the photon, or just along the direction?
It's transfers to the beam, to the beam direction. That would be, the electron nucleus beam, just like we do.
Okay, this is not the so this is not really in HERMES data. HERMES data they analyze in the bread frame. There, the transverse momentum is perpendicular to the photon direction.
Yes, I understand that, and I did not address the transverse momentum.
Okay, so this is more or less like the Z, right? But you also have Z here, right?
Yes.
So what is
Z is the same. It's the fragmentation. So if you have a momentum, right? You have a longitudinal momentum. You have a transverse momentum, and the Z still is the fragmentation fraction, right? Now, no matter what frame we measure, we will still have a fragmentation fraction.
Okay, so you have some kind of suppression both as a function of Z and also as a function of PT. And this PT is not necessarily in the PT
it's not at all in the it's not at all in the braid frame.
It's not there.
No.
Okay.
It's in the collision mode. The first approximation, we'll call it on a line. We know that, some epsilon angle at which the beams will intersect the DIC.
So if I want to look at the PT broadening, this is not the PT you're looking at.
No.
Okay.
No. The PTs in the braid frame, of course, will be much smaller, right?
Okay.
And they were very small, right, at HERMES, going to about a GeV, creeping slowly or something like that. This is a very different PT, very similar to the collider physics that we do. So I wanted to explain.
May I ask a question too here?
Yeah.
So do you get enhancement for small PT for D meson and B meson?
Not in the region. You kind of can see it a little bit right here for the B meson, but we figured out that the kinematics is such that, I have to go, let's see how much I have to go back. Yeah, all right. So kind of when you go to this small Z region, it doesn't contribute all that much to the cross section. The kinematics is such that in terms of PT, when you look at PT, you're integrating over Z, and then you don't see it much. If you do it differentially over Z, you'll see it. That's one of the points. But as a function of PT, simply because you're integrating over a larger Z region, you don't see it, right? You can see just a little bit when you're pretty much, because of the low center of mass energies, you're kind of forced to particular values of Z when you look as a function of PT. When you go to more relaxed kinematics, that was the point of this upper figure here. You are going to see still suppression of pions, as I showed pretty much everywhere within reasonable Z. We have large suppression. So pions are still suppressed by about a factor of 2. But you see what happens to DMB mesons, right? Kind of their suppression starts to be comparable with 1. And the reason is that when kinematics doesn't force you in a particular corner of Z space, then you're kind of sensitive to this transition region when it goes from suppression to enhancement. And that's the reason for which for D and B mesons, you see it like that.
Yeah, yeah, maybe this is depends on detail of how you implement it, but I always have naive kind of expectation, say that heavy flavor has to be conserved. So in the sense, you initially produce a C quark or B quark, in the end, it end up with the D meson or B meson, right?
Yes.
So the total number should not be changed dramatically.
Yes, but they may not be in the acceptance that you see, right? I mean, if they are shifted to lower PT where I cannot calculate it perturbatively, right? Then we won't be able to see it. I'll show you that we can see it as a function of Z, where I keep the PT, and the fact that I can go to lower Z is simply because the Parton energy will grow. But before I show you that, I want to make one last comment, why the difference, right, between forward rapidity, small center of mass energies, large rapidity, backward rapidity, large center of mass energies. The reason is that because of the LPM effect, the strength of energy loss or in medium showers depends on the energy of the quark nu in the rest frame of the nucleus. And in order to do that, let's say you have some fixed PT, right, that you can calculate perturbatively. The energy would be PT times cosh of the rapidity gap between where the nucleus will end up and where your measurement is. So you can minimize this gap two different ways. Go to low center of mass energies and forward rapidities. When we go to large center of mass energies and backward rapidities, then the rapidity gap is so large, cosh delta Y is such a huge number that you're simply killing the contribution for the medium Parton shower. Now, I explained, as Frank said, well, you know, kind of what happens to the DMB mesons. I explained why here you're not seeing much effect for them. So essentially, you're not using them to their full potential. In order to do that, you have to look differentially in addition as a function of the momentum fraction Z. And here you actually see it. When we look at the pions, we always see suppression of pions, right, which grows at forward rapidity. But so just by using pions, we cannot differentiate between those models of in medium absorption and, you know, evolution in medium perturbative calculations and energy loss. But if we go to DMB mesons, what you see is, you know, the clear transition from suppression at large Z to enhancement at intermediate Z. And because I cannot normalize everything, that's more differential than my denominator. Of course, you know, there will be some differences which I cannot completely cancel from initial state nuclear effects of shadowing. But, you know, this is still a clear discriminator between the two mechanisms. And I have literally asked Will Brooks, what happens to the D mesons, right? You know, kind of to the soft D mesons in those absorption calculations, right? Which give suppression and or the pions or protons for that matter. And he answered, they simply disappear from the acceptance. So that was the answer. So those absorption models are not very differential. This in principle will account from any enhancement that you saw in the splitting functions. The question is only whether you'll see it in the kinematic region where you can calculate perturbatively. So I hope this answers the question. And so with this, let me move to jets. Finally, we're ready to move to the jets. Now, jet production can be calculated various different ways. One way to calculate it is to use semi-inclusive jet functions. And the idea of the semi-inclusive jet function is to take a hard-struck parton and then fragment it into a jet. So the factorization formula in this sense is very similar to hadron production, just the fragmentation function is substituted with a semi-inclusive jet function. Because the jet has a structure, it has a radius, it has transverse momentum of the radiation limited to, let's say, PTR, a new scale emerges in addition to the hard scale, where we can take it to be PT, we have a jet scale, which is PTR. And if R is 1, we don't have to worry about it. But if R becomes small, then we have hierarchy of scales. And to improve the precision, we can do resummation. Turns out that this is Diglap evolution between those two scales, which allows us to resum large logs of 1 over the jet radius when the radius is small. And this figure shows that indeed there is a difference between an analog calculation, which may underestimate, in fact, theoretical uncertainties, and a calculation which includes leading log resummation in R. When we go to smaller transverse momenta, the differences are less pronounced between the two, but nevertheless, it is useful to include and improve the precision of the baseline calculation of jets in electron-proton collisions. And this is what is done. With this, we move to the evaluation of the jet in the medium, and what we have to calculate is the semi-inclusive jet function in case of nuclear matter. So this would be the diagrams which contribute to the semi-inclusive jet function to one loop. And if we take one of them and embed it in the medium, we will start getting interactions like the ones that I have shown. And it really doesn't take too much looking to realize that these are in fact the in-medium splitting functions. Incidentally, the jet functions can be written in terms of splitting functions. So here are how those jet functions would look like. This is for the case of a quark. This is for the case of a gluon. And these are the in-medium splitting kernels here. We have normalized by some of the Z dependence. That's why we've called it H as opposed to P. And those have to be understood in terms of distributions. They have to be convolved with the hard part, or the cross section, to produce a hard parton. We can also do power counting in alpha to see which terms we have to take contributing to the cross section. One thing that I have to point out is that while the baseline jet cross section includes resummation of the logarithms of the radius, we have not done that for the case of jets. So the case of jets, it would be a fixed order calculation. So it would be strictly an analog contribution for the case of the medium. Okay, so on to the physics and the results for jets at the EIC. To study jet production and jet modification, we define the ratio, the nuclear modification ratio, as a function of PT in a certain rapidity bin, and the normalization is 1 over the number of nucleons. This is a trivial normalization, to have apples to apples comparison. It's equivalent to TAA in the case of, let's say, heavy ion collisions, or the number of binary collisions. We have 2 types of nuclear effects which will play a role. Some of them are initial state effects, which might be parameterizable as nuclear Parton distributions if they're leading twist. And then we have final state effects from the interactions of the jets in the medium and the medium-induced Parton shower. And a strategy to emphasize those would be to vary the jet radius. As I emphasized at the very beginning, the main physics comes from the fact that in-medium Parton showers are softer and broader. So by selecting a small jet radius, you might still capture most of the vacuum shower, but eliminate most of the medium-induced one. And this will lead to a suppression of the cross-section. So the basic results here taken at this highest energy for an intermediate radius and at forward rapidity, we know that forward rapidity is useful, of course, are given in those 2 panels. The upper panel shows you differentially the contribution from initial state effects, that would be the nuclear PDF. We're essentially transitioning from small anti-shadowing to the EMC effect at high PT, and the EMC effect is large, it's almost 30%. And the green band shows the contribution of final states only. At low PT, we have 10 to 20% effect, but as we go up in PT, this disappears because the energy of the parton in the rest frame of the nucleus grows and the medium-induced Parton shower contribution is small. The total effect is given by the red band. It includes uncertainties, variations of scales, and you see that the effect is actually large, 20 to 30%, and it will be easily measurable at the EIC. The other thing that was suggested to us to look is what are the differences between the different Parton distribution functions. And on top of NCTEC 15, we included EPPS 16. And here is this ratio. And you see that the absolute difference between the two parameterizations is less than 5%. And they have essentially the same shape. This is because I assume, the EMC effect is well known and well parameterized in the valence quark region. And as you can see, they're essentially identical. Of course, we will learn more about nuclear PDFs at the EIC through inclusive measurements and variety of other measurements. But if we measure such a modification, then the question becomes, how do we separate these initial and final state effects, not only theoretically, but through an experimental measurement? And so here is how we can do this. We can look at the nuclear modification for the two different radii and create a double ratio. That would be the suppression of a jet of finite and, hopefully small radius r, divided by the suppression of a jet for a large radius r equals 1. The idea of r equals 1 is that it will capture most of the final state shower, so the medium modification would be minimal. But the double ratio will cancel initial state effects, which are identical. We can actually look and see that it works. The bottom panel is what has to be compared to the previous figure. And you see that now we have eliminated this initial state effect that led to this behavior. And we only have final state effects from the in-medium Parton shower. And you also see that there is a hierarchy of suppression, which is the largest for the smaller jet radii. Of course, if we want to enhance the effect, we have to go to somewhat smaller center of mass energies, such as 10 on 100. And in this case, the separation is much bigger. And also the suppression is close to a factor of 2. It's actually quite spectacular. We have factor of 2 suppression in the case of heavy ion collisions. And of course, here it's facilitated by the falling spectra, the transport properties of different, but this would be something measurable and very exciting to study. So before I move on, one final check that indeed we can separate initial and final state effects. We've repeated the calculation with EPPS 16 and NCTEC 15 for various radii, and you see that for all radii, the difference is less than 5%. And here you see the double ratio that I showed on the previous plot with 3 different radii and the 2 different parameterizations. You literally cannot see the difference between the dashed line and the solid line, which means that initial state nPDF effects are completely canceled. So we indeed can make this type of measurements at the EIC. So the final topic, jet substructure at the EIC. As we know, and in fact that was predicted well before it was measured, any modification of inclusive or tech jet cross sections, if our theory is correct, will be associated with modification of the jet substructure. And jet substructure is simply a modern way of saying jet shapes, jet fragmentation functions, or jet charge. And the one illustration that we decided to do is for the jet charge, which is defined here. The jet charge is the the charge-weighted PT of the hadrons inside the jets to a power kappa. Kappa has to be positive for infrared safety. We can vary kappa, and we can vary the contribution of soft versus hard particles to this observable. That's what in practice it does when we vary it. And the jet charge is simply a proxy for the charge, electric charge of the Parton. And it has been used quite extensively to determine the Pertonic origin of jets. More recently, it was studied in the framework of soft collinear effective theory. It started with the following definition for the average jet charge. And essentially by integrating here over the momentum fractions z, the sum becomes an integral, we can finally get a very simple factorization formula. It is the kappa plus first Mellin moment of the matching coefficient divided by the inclusive jet function and the kappa plus first moment of the charge-weighted fragmentation function. So the question is, why only quarks enter? The reason is because to the order to which we calculate, gluons don't have an electric charge and they do not contribute. What is interesting is that, of course, then we can study the scaling violations of this observable, and they are related to the scaling violations of the charge-weighted fragmentation function. And by measuring, for example, the scale or PT dependence of the jet charge, we can directly extract moments, Mellin moments of the splitting functions in QCD. In fact, that was done at the LHC by the Atlas collaboration. They did many things. They were also, by using dye jets, able to separate up quark jets and down quark jets, perform measurements of the average jet charge, sorry, it's not average, it's flavor separated jet charge for different values of kappa, and you see how the calculations that Haitauli did using the soft collinear effective field theory framework actually describe reasonably well the jet charge for different values of kappa for up and down jets. When we move to the jet charge in the medium, as I mentioned earlier, the different components of factorization formulas receive medium-induced contributions. And I apologize for using those formulas from a previous presentation for AA collisions, because the jet charge only includes final state components. That would be the jet, the matching coefficient, the inclusive jet function, the fragmentation. It really doesn't matter if I label it PP and AA versus EP and TA. It's exactly the same. So here is how we calculate those contributions. The fragmentation functions, whether they're charge-weighted or not, receive a medium-induced evolution, medium-induced contribution. There is a contribution to the jet matching coefficient, which is expressed in terms of splitting kernels that we've calculated previously. There are upper limits of the integration, so this automatically takes into account jet quenching. And finally, by adding the matching coefficients, weighing them by the momentum fraction and integrating, we get the total inclusive jet function, which is the normalization in the denominator. This is the final formula for the modified jet charge in EA versus EP collisions. And we can even study the scaling violations as a function of the transverse momentum. So here is the phenomenology. This is what we obtain for flavor isolated jet charge in the upper panel and the average jet charge in the lower panel in electron nucleus versus electron proton collisions. Since in the upper panel, we've already assumed we can do flavor separation through experimental techniques, what we are looking at is directly the contribution from in-medium scaling violations. You are literally looking at the effect of the in-medium Parton shower. Of course, it's the largest for small PT and gradually becomes smaller at large PT. It's not gigantic, it's on the order of 10% or less, but this is something that would be very exciting to measure precisely at the EIC. When we look at all jets, look at the average jet charge, we're probing a different type of physics. The physics here is that the nucleus contains protons and neutrons with different mix of up and down quarks. So studying this charge, the charge is actually a difference of contributions with different signs. So the evolution effects will be much smaller, right? They're overlapping, they're suppressed. However, the overall effect, 0.7, that's a 30% effect, it's large. And it can help fitting nuclear PDFs and looking at isospin violations at large BRK max. And this is where I think the average jet charge would be the most useful. So before I conclude, let me make one last comment. EIC is not the only proposed electron-ion collider. Now, the difference is that the EIC is almost on shell. I mean, it is on shell. But there are other proposed facilities like the Large Hadron Electron Collider, or even the FCC will probably have the ability to do some electron-hadron collisions. And then there is a proposed electron-ion collider in China, EICC. Now, at the LHEC, the center of mass energies that you get with those nuclear and electron beams are so huge that no matter where you look at in rapidity, the effects of final state interactions and medium-induced Parton showers and cold nuclear matter, they will just be non-existent. They'll be completely power suppressed. So such a facility would be good to study nuclear PDFs and small x physics, gluon saturation, but definitely not hadronization. On the other hand, the electron-ion collider in China, here is a schematic. It looks quite complicated, but I don't know anything about collider facilities. It's proposed to be built in 2 stages, EICC1 and EICC2. And these are the 2 center of mass energies compared to HERMES, COMPASS, and the EIC. ERIC is now EIC. This is an older figure. And you see that the center of mass energies are in fact ideal to study energy loss and hadronization and nuclear effects. But the electron-ion collider in China will be limited in its ability to study saturation physics. So this brings me to the conclusions. So jet physics in EPNTA is an important part of the EIC program. It can provide information about nuclear PDFs, hadronization, transport of energy and matter in the nuclear environment, in addition to all the other topics that we talked about, saturation, TMDs, etc. So we developed a theoretical approach to study the medium Parton showers, numerical tools for their evaluation, and we also figured out on a somewhat simpler calculation, which was the hadrons, that the best way to study this physics is to go to lower center of mass energies and forward rapidities, and high luminosities, of course, would be beneficial, especially when we start studying substructure, small signals, or go to heavy flavor jets. So we did a calculation of light and heavy hadrons and jet substructure. And what we found that the modifications are significant. So they'll be measurable at the EIC. Of course, if you look in the right phase space for them. We also developed the strategies to separate those initial state from final state effects and to facilitate both the extraction of nuclear PDFs and cold nuclear matter tomography, and also help with flavor separation, studying in-medium scaling violations or isospin symmetry breaking. And finally, there is this comment where EIC falls, and it does seem indeed to occupy an ideal middle ground, allowing studies both of phenomena at very high energy, such as gluon saturation, but also at lower energies, such as Parton energy loss and hadronization. And so with this, I thank you, and I'm ready to take questions if you have some.
Well, thank you, Ivan, for such a comprehensive talk on JET at EIC. And I'm sure there should be a lot of questions. Yes. The first question comes from we all.
Oh, hi. Hi, Ivan, thanks for the talk. At the very beginning, you mentioned that depending on the energy of the hard process, there are either hadronization inside the nucleus, or there's a case that you have a vacuum hadronization outside of nucleus. So from all these observables you talked about, what do you think might be for the signature to distinguish between these 2 type of scenario, like something like a function of beam energy would be?
Yes, so okay, let me try to again repeat. So the histories, and kind of Xinyan has worked on this, Francois Leoch has worked on this from the point of view of energy loss, Alberto Accardi, Boris Kupeljovic, from the point of view of hadronization, in medium hadronization. One can assume, I'm more familiar, of course, to the energy loss part. I've done this type of physics, I can relate to it. The model, sorry, that's the energy loss and in medium showers. The in medium hadronization, I'm not an expert. Probably that's the best way of saying it. For example, what happens to those hadrons when they're absorbed, right? We had this little discussion with Fang, where do they go? I said I've asked questions. The answer is they go out of the acceptance. I think this model is a bit less detailed. Perhaps it's detailed to those who know it. What I said is that at the EIC, I think the first case will be more relevant. I was talking about how high the Parton energy is in the rest frame of the nucleus. And essentially the problem for us is that the energy is so high that, kind of the final state Parton showers effects can be small. Now, if my physics intuition is correct, I mean, you can think of the hadron, let's say the hadron had a certain formation time. Let's call it a Fermi. We can argue that it's half a Fermi, doesn't matter. But then it's boosted by the energy. And because this Parton at the EIC will have much larger energy, I think this would be the more relevant picture. There is one exception. The exception is for heavy flavor. In those formation times, the mass of the heavy flavor will come in the denominator of formation times. And if you go to, for example, DMB mesons, the formation times can be shorter and in principle still fall within the size of a nuclear length. Let's call it 5 Fermi. So here comes the idea that we can use DMB mesons to differentiate. The purpose of this calculation here was to show that even after we convolute with the PDFs and the hard part, if we take initial state effects into account, we will see this transition from enhancement, from suppression to enhancement, very pronounced for B mesons, but pronounced even for D mesons. On the other hand, if what I understood correctly about hadron absorption is true, then DMB mesons will always be suppressed as a function of the momentum fraction Z. And that would be something very useful to try and differentiate. Now, I do not know how hadron absorption models will evolve, whether they'll come up with a model which also mimics this. I don't know. At present, I think the claim is that just the hadrons are absorbed. So I would say that would be a one way of distinguishing. Sorry if the answer was too long. But that was the essential usefulness of measuring DMB meson modification.
Thank you for the very detailed answer.
Okay, Peter.
Yeah, hi, Ivan. Thanks for the talk. I actually have a question, not about the EIC, but about calculation. You talked about sort of halfway through this paper that's coming out this evening about deflection and matter.
Yes, it is right here. That's like this one slide.
There we go. Yeah. So that actually your description went a little quick for me. In fact, as perhaps you recall, I talk about these things. We've been trying to make exactly these kinds of measurements. If I've understood what you're calculating, in particular, trying to push down the jet PT, kind of intuited that you seem to have some justifications for that, and your number of 10 GeV certainly caught my attention. We are trying to measure in that vicinity. So can you say a little more about the calculation and what really goes into it? And just to remind you, and Fang and others have done work on this, there are actually QCD backgrounds to any such process due to Sudakov radiation that have to be taken into account that mask these deflection effects. Can you say a little bit about the ingredients and phenomenology and whether we can compare to experiment, if not, what's needed in order to compare to experiment? Well,
right away, I'll tell you that to compare to experiment, we have to think how more quantitatively, how large they are. We did a parametric estimate. So this is a paper with Andrei Sadovyev and Matt Sievert. It's a purely theoretical paper. It's 80 pages long, so I apologize. So you're better off, reading the introduction where we put some selected results and then the conclusions. But what we did is we relaxed the assumption that, the scattering centers, we put motion directly into the scattering centers, and then went through the whole calculation of how this motion is transferred. It's not simply assuming, people have done in the past, some arguments that it's simply a shift of Q0 in some distribution, which is actually incorrect. Let me not comment on that. I'll tell you what we did. We put the motion directly in the particles, in the Lagrangian, calculated everything, and calculated things to first order in opacity. We included the effect of constant velocity. Let's say the medium moves at least locally with a constant velocity, but we also included the effects of gradients in velocity and also the density of the medium. The parametric estimates are given. What we found is that the RMS broadening of the jet, when you shoot a jet through the medium and it scatters, you get some RMS broadening, right? This is the Gaussian part, and then there's some power law contribution from the tails of the Maurer scattering. We found that the RMS broadening is not changed. In a sense, the jet does not become broader on average, if you want, or fatter. It just gets deflected. We found that not only the linear moment of the jet deflection is generated, it also generates odd harmonics. All odd moments are changed. We're still trying to think what implications there will be. But if there are medium fluctuations, if there's medium motion, so we expect that the jets will be deflected from being exactly back to back. Well, now I just said that if you're doing correlation measurements on an event-by-event basis, I think, well, I don't know if you can, on an event-by-event basis, you might be able to detect the deflection. On average, it probably will be just additional component to the broadening. So maybe one is better off looking at those things on an event-by-event basis. As I said, we've not thought very carefully about phenomenology. We just wanted to, cross the T's and dot the I's on like 80 pages of formulas. The other thing that we looked at is the effect on the radiation of jets. And what we found is that the medium, if we look at this illustrative formula here, K perp XE is just omega, the energy of the gluon. K perp is the angle relative to the jet. So you see that the effect will be largest for the large angle emitted gluons. So it seems that kind of the flow can affect things near the periphery of the jet. That would be something interesting to study. We also saw this emergence of kind of linear moments or odd moments in the radiation spectrum. And so, we know that the jet will bend, but also there will be more gluons preferentially emitted in the direction of the flow. So this is kind of what this cartoon with 3 gluons on one side and only 1 on the other is supposed to show. So these are the results that we have. The formalism is there, the derivation is there, and we'll be thinking, it seems that Andrei is interested in, the phenomenology of it, and also Matt Sievert a little bit. So we'll see how it goes. But, kind of this summarizes what we have done.
Okay, thanks. I think there's much to discuss about the phenomenology, but let's take it offline. I'll send you an email. Thanks, Stephen.
Okay, great. But I think those are interesting results. Like at the beginning, it was not clear to me where it will lead, but finally we managed to synthesize things into formulas about shifts and even if they're pocket formulas, they allow us to estimate things.
Well, let me see. Well, there is a, let me ask a question while other people still maybe have other things. That's just one comment expect on this. In fact, in our latest study we published last year, you can actually look at the PD broadening with no flow, but with gradients. If your Q hat, for example, or the density along perpendicular direction has a density gradients, and let's say the density become smaller as you go up, right? It has the same kind of deflection. This is what we call a gradient. In fact, we proposed so-called gradient tomography so that we can use this deflection to trick on the initial production point in heavy ion collisions.
Okay, so I haven't looked at it, so I have to look whether it's from a theoretical point of view or you studied in a model the effect. What we did is we did calculate, and yes, in principle, we found that gradients also lead to deflection, but they lead to specific moments. Also, I think the effects were on odd moments. In order to be able to calculate them, one had to, you know, if you strictly start with a delta function, we're getting technical with a delta function distribution, you know, we cannot calculate it easily. We'll start, you know, kind of breaking kinematics, but you have to assume like a wave packet. If you assume a little Gaussian wave packet, then you can actually, you know, kind of, you have leeway, so to speak.
What we did is very simple. What we did is very simple. We just look at the Boltzmann transport equation and they introduce some kind of gradient in the density, and then you automatically have this out.
Okay, so it's through simulation. We here did it through the calculation, and I have to say that, you know, kind of, because this is much more involved to get radiation, the gradients in density and velocity, we have both. Gradients in density and velocity, we were able to do fully on the case of jets, not radiation.
So my comment is actually, is a question actually, is that, is this your result equivalent to a situation where I do this calculation in a co-moving frame, and later on I just do a boost to the lab frame with this flow velocity? It should be equivalent, right?
I think for local interactions, yes. But I think if you have to take into account a coherence over long distances, I'm not 100% sure, right? Because you have to be doing changes depending on the frame at every point.
Well, I think not wise, because the formation time is essentially in normal, most of, I mean, the interference effect, long correlation, because of formation time is in the longitudinal direction. Here, you only just have transverse boost, which should not be, you know, influenced by that.
No, but if it varies, right? So in principle, you can express those as integral quantities. Of course, the illustrations here in those formulas are for a constant one.
Yeah, but I can tell you, there is such effect. I mean, in our monocolor simulation, in our linear Boltzmann model, we essentially did exactly this. For every collision and radiation, we simply do that in the co-moving frame, and then after each collision, we move back to the lab frame, and we see this effect. We see both the gradients, you know, density. We also see the flow effect on both the elastic scattering and also radiation. The question is whether those results are equivalent to what you have here.
Well, that one I cannot answer, right? If we're able to do a simulation, we can see that. As I said, this is, you know, kind of strictly a theoretical derivation.
Yeah. Okay.
Let's maybe a follow-up.
Probably can take this offline, you know, maybe next time, because this is interesting to me too. So we will continue discussing maybe through email.
Mm-hmm.
Do you have any other comment?
Oh yeah, just one follow-up comments of yours. So I'm also curious whether this extra term can be like absorbed into that if you put a motion in that the scattering cross sections.
I tend to, for example, Ivan, if you look at your formula one in the co-moving frame, and then what you can do a boost in a transverse direction, and then in that boost you simply expand in terms of velocity and only look at the linear term, which could be equivalent to what you have.
It could be. I'll tell you, okay, since we're going in a very detailed discussion, let me tell you that we've thought about this, and you know, kind of we didn't see immediately an easy way to absorb those things. And let me tell you exactly what I mean. About 15 years ago, certain authors simply made a model of you know, kind of shifting everything by a certain momentum Q naught.
Yeah, oh, that's
and
not,
so,
of course,
you know,
that's not trivial. Yeah, yeah.
And it turned out that the calculation is, well, there's no calculation, sorry. It turned out that the conjunction, not conjunction, what the hell is it called? The conjecture is incorrect. And you can actually prove it if you simply looked in this model where you can have a Q naught, just like that, boom, Q naught. You can actually describe this as a shift of the radiation around a new position. Right? Here, those terms don't have the exact same structure, so it's not equivalent. This is not equivalent. You know, it could have been a shift if they were exactly the same, but they turned out not to be. So what we figured out is that if you actually look at scattering centers of the medium and look at their velocity, turns out that you cannot simply assume that there is a Q naught, that there is simply no way to derive it. So we have to think in terms of velocity and do this derivation. And I was trying very hard to see if there is such an equivalence where I can proclaim this to be exactly the same distribution, just around a new position. And we were not able to do that. So we have to think more about it. So, yeah.
I think it should be, maybe, you know, it would be nice if you can think about this. And I believe there could be some connection here.
I'm sure that there is something, right? But as I said, when we derived and we isolated the terms, this is what we found, and that's the best we have.
Yeah.
So.
Okay, great. Okay, let me see if there is no other questions. I think we already have, you know, passed like 15 minutes past our time here.
Yeah, sorry.
So let's stop here. And I would like to thank you again for such a great talk. And then, you know, apparently we have a lot of interest, in your work here.
Okay, great. Thanks, guys. Again, thanks.
Okay.
Bye-bye.
Thank you.
Okay. Thank you. Bye-bye.
Bye-bye.